What's going on, everybody? It's Mr. Gus, and I'm in the physics conference room. Today we're doing a lab. We're going to do a lab about resistivity, okay? Now, resistivity is something we can measure. It's related to the content of the material that creates the resistor. It's related to the length of that resistor, and it's related to the cross-sectional area of that resistor, okay? So there's a relationship between resistance, or total resistance of an object, and the material it's made out of, the shape and size of that object. So today, we're going to look at one. Now, we're going to do something kind of crazy because we can always use the resistors in class, but if we use the resistors in class, they kind of have a stamp on them that tells us what the resistance is. So we're going to try something a little differently. We're actually going to use a pencil, and you can actually do this at home if you have a pencil and you have a multimeter. Check your garage for a multimeter. Ask your parents if they have one. We got one at my house. It helps us do electrical stuff around the house. So you may have a multimeter at home. If not, go to Home Depot, grab one. They're pretty cheap. Ask or order on Amazon. Here's the deal. All right, the graphite actually in this pencil, not the pencil itself, not the eraser, but the graphite, the carbon sheets that make up this graphite are conductive. They have a resistance to them, a pretty high resistance. They're not metallic by any means, but they behave metallically. They've got some kind of metallic property that will allow electrons to flow through them. So we can actually use the graphite in our pencil and kind of make a resistor from pencil graphite. So here's what we're gonna do. I'm gonna go ahead and I got my setup right here. I've got my ruler. I'm gonna go ahead and sketch a line that is 10 centimeters long, okay? So let's go 10 centimeters all the way here. Make sure it's a pretty straight line. And then you wanna really kind of make it dark. Get a lot of material on there, okay? And then we wanna make it a little bit wider. So this is pretty narrow. I'm certain I'll be able to get some good data from it, but let's make it just a little bit thicker, wider, so that we can make sure when we do our lab that we really get a good resistor for us, okay? So you can kind of see this really thick line right here, okay? And now what we're gonna do is actually mark off every centimeter for about 10 centimeters, all right? So we'll start here. We'll call this one right here 0. And then we'll call this 1, there's 2, that's 3, 4, 5, 6, 7, 8, 9, and this is going to be 10 centimeters. Now I've got different lengths of this thing here, and you can kind of see if I hold it up, you can see what I got set up here, right? I got 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, and a really dark line made from graphite. You can't use a colored pencil or a charcoal pencil. Graphite is going to be the thing that's going to work the best here, okay? So now here's what we're going to do. In order to do this, I've got my multimeter set up. Obviously, I've got a wire in the common ground. Always ground my stuff. I also have it set up. Over here are our 2 current readers, right? This is where the current, we measure amps over here. Well, over here in this terminal is where we measure our voltage or potential difference. It's also where we measure our resistance. Then you're going to turn the dial. I actually had to figure this out the hard way. This is a pretty resistive line. So I've actually turned all the way. I'm not in ohms. I'm not in 2,000 ohms. I'm not in kilo ohms. I'm in mega ohms. I'm all the way up here. And if you look at your equation sheet, megas times 10 to the 6. There's a lot of resistance in this line here. All right. So I've got that set up. Now this thing is going to produce, probably because it's in the potential difference, it'll produce a potential difference across this line, do a quick calculation, figure out what the resistance is for us, and that resistance will show up here, but it's going to show up in mega ohms. Don't forget it. So let's look at our data table. I've got the graph. I'm going to change the length of my wire, or the length of my line. So I'll measure at different lengths, and then it will read out resistance. So my resistance is on my y-axis, my length difference is on my x-axis, and here are the 9 lengths I'm going to do. I'm going to go from 1 centimeter all the way to 9 centimeters and get the resistance there. So your job is to track those changes. Let's go ahead and get some data, okay? So the way I would do this is I would go ahead and I would put my probe at 0, and then I'm going to hold this probe here the whole time. All right, let's hold it here the whole time, and then we'll use this other probe and we'll change down the line. You can kind of keep track of this data. All right, so at 0 to 1, so over 1 centimeter, it's 0.03. again, that's mega ohms. Okay? Mega ohms. Maybe I should stop getting off the board. I'll just write these things down. Okay? So 0 is there at 2, 0.06, at 3, 0.09. Oh, I'm seeing a pattern. 0.13. 0.18. 0.4. 0.3. 0.34. 0.38. All the way down. Well, this is 10, so actually we're way past this thing. I'm wondering now if I could have done it at 200 ohms, maybe. I didn't think I could. Oh, I totally could have. Oh well. All right. Let's record our data now. Okay. Here we go. This first one is 0.03, 0.06, 0.09, 0.13, 0.18, 0.24, 0.3, 0.34, and 0.38. And again, these are all times 10 to the 6th because they're in mega ohms. So, all right, that's some data I'm going to ask you to graph in your lab. The last thing I'm going to tell you is it looks like, just by looking at the data, it looks like there are certain increments it goes up by every centimeter. So that's important. So we should get a line, right? When I get this data, I should get a line. Okay? So it looks like I'm going to end up with a line like this. Now, if I look at my equation sheet says this. Total resistance of an object is equal to the resistivity of that object. This resistivity is unique to the material. I don't want to say it's a constant because resistivity can change with temperature and pressure and stuff like that, but the resistivity is unique to the material at a certain temperature and pressure, okay? So this is true. Now, if I'm looking at this equation in the graph is a line, I want to figure out what is this slope going to be. I'm not sure what the value of this slope is. I have an idea, but I'm not certain. I haven't graphed it yet. What will the slope tell me? Well, my equation is a line. A line always takes the form of y equals mx plus b. Okay? Now there's no y-intercept. Let's get rid of that. So my y variable, or my dependent variable in this case, is resistance. So that's my y variable. My independent variable is length, or L in this case, L. My slope is whatever is left. If I look at my equation, I see resistivity and area. So what's left over? Resistivity over area. What is my slope going to tell me? My slope should tell me the ratio of the resistivity of this object to the cross-sectional area. So once we get our slope, we're even a little bit closer to finding what is the exact resistivity of the graphite in our pencil. Your job is to go figure that out. All right, if you got questions, drop in the comments, send me an email, ask me in class. Until next time, see ya.